Hi everybody. Hi Annalisa. Take a look at this. We're going to talk about the isosceles triangle theorem today. I got a lot of questions I want to show you here. But this page starts off with, use the back of this page to prove the isosceles triangle theorem, proving the biconditional. So we got a couple things to do. We are to prove that AB, these two sides are going to be congruent if and only if this angle at A is congruent to this angle at C. Let's take a look at that right away. I'm kind of set up to do that right here. You might want to make a sketch like this ahead of time. A couple things I want you to know before we get started. There's a couple symbols that will make life a little bit better for us if we know about them ahead of time. This upside down A, in a math class, that means for every. You'd be surprised how often you could get a chance to use a symbol like that one. This backwards E, I did not make this up. That stands for there exists. Very commonly used in a math class. A couple of things are. Those couple of symbols are. We're going to prove this. Two sides of a triangle are congruent if and only if the angles opposite are congruent. You see, it's a biconditional, this isosceles triangle theorem. We've got to prove it coming and going. Come in the first place, we're going to, given that two sides are congruent, let's say that AB is congruent to BC. Mark it that way ahead of time. We're going to prove that angle A is congruent to angle C. And what we've seen lately, what we know well to do is to get a couple of congruent triangles and talk about their corresponding parts. But here we don't have that. But we can make that happen. Here's the nice way to get this proof done. Show M the midpoint of AC. I'm going to call that place M right there. And over here say, show M midpoint of AC. You might be saying over here, well, you better have a good reason for that. What makes you so sure that AC even has a midpoint? I say, well, for every segment there exists a midpoint. And that's true. For every segment there exists a midpoint. And I declare the midpoint of AC to be M. I want to get a couple of congruent triangles here. Statement 3. Show BM. When I show that segment down the middle, you might be saying, well, what makes you think you can go around showing that segment BM? I know B was there and M was there, but what makes you think BM would exist? And I would tell you, well, for any 2 points, there exists a line. For every 2 points, there exists one line. And I'm just going to show that part of that line. Now, with the things we've got built, I bet you I can get a pair of congruent triangles here right away. Working on getting these triangles to be congruent. We did make M be the midpoint of AC. That tells me right away that AM would be congruent to MC. You guys say, well, what makes you so sure? Just because M's the midpoint that these would be congruent? I said, well, that's what midpoints do. I'll call that the definition of midpoint. Try to get those triangles to be congruent. Maybe you got a way we could. I don't know about these angles yet. That's what I want to prove. But BM is congruent to itself. Very helpful. That's our friend's reflexive property. Make that note. BM congruent to BM. With that thought in mind, reflexive property of congruence. Reflexive property of congruence. He exclaims. Now I've got congruent triangles, don't I? Make a note about that. Triangle AMB. Congruent with its partner, triangle CMB. How'd you get those triangles to be congruent anyway? Well, all the sides of this one match all the sides of that one. Let's call that side, side, side. And now that I have congruent triangles, might we think that the angle at A is going to match the angle at C? Yeah. Those base angles are going to be congruent, aren't they? So angle A is congruent with angle C. And that's because the corresponding parts of congruent triangles are congruent. So now I know when two sides of a triangle are congruent, then the base angles must be congruent. I tell you what, this proof would be a great proof to put on your next test that you're probably going to have this week. You don't have to use the upside down A or the backwards E, but you got to talk about for every segment there's a midpoint, and for every 2 points there's a line. And get that proof figured out. That's a good one to memorize. We're going to look at the other half of that proof right now, since it was a biconditional. This time, I'm given that these angles are congruent. The base angles are congruent. And if those two angles are congruent, does it have to be isosceles? And I'm telling you it does, but let's see how we can make that happen. This proof's a little bit like the last one. Again, I want to get a couple of congruent triangles here, but I don't want to go for a midpoint this time. But I do want to divide this into a couple of congruent triangles. Do you think that every angle in the world has a bisector? I think so. I'm going to say show BD, the bisector of angle ABC. Show this line, show BD so that it bisects that angle. Call that place D right there. Now what makes you think that ABD, this angle, even has a bisector? I said, well, every angle has a bisector. All right, we can use that thought. For every angle, there exists a bisector. Now, you don't have to write it like that, but that makes sense to me. For every angle, there exists a bisector. So I could show BD the bisector of angle ABC. And when I show that, it makes me think, well, these couple angles must be congruent. Let's make a note about that. And it would be okay if you put a 1 here and a 2 there. So we can talk about them quickly and easily. Angle 1 is congruent with angle 2. Why would that be true? And if it is an angle bisector, then that angle's been congruent, divided into congruent parts, because the definition of an angle bisector does what an angle bisector is supposed to do. Now, can we get these triangles congruent anyway? I've got a couple of angles here, congruent to a couple of angles there, but I need to get a pair of sides. I'm proving that these sides are congruent. I do not know that yet. However, what about BD being congruent to itself? Would that be fruitful? I think it would be. I'm going to make that note. BD is congruent to BD. My friend, a reflexive property. Reflexive property of congruence. So now, have we got congruent triangles? And it's not one of the first postulates that you learn, but angle, angle, side, matching angle, angle, side makes me think these must be congruent. I'll say it's triangle time, triangle. I call mine triangle ABD. Is congruent with triangle CBD. Right, angle, angle, side. You might be thinking if these two angles here match those two angles right there, then the third pair of angles would be congruent, and that would get the triangles to be congruent by angle, side, angle. But I like angle, angle, side works just as great. Let's finish this proof up. Oh, step 6. If these triangles are congruent, is it safe for me to conclude that AB from this triangle corresponds with CB from that one? Yeah, those are corresponding parts of congruent triangles. They got to be congruent. So I know that the isosceles triangle theorem is valid. Two sides of a triangle are congruent if and only if the angles opposite them are congruent. Now I've got a couple of questions I'll work through with you. We've done this proof. Let's just play with a couple of these figures. Triangle PQR is isosceles with base PR. If this is the base, we ought to mark the legs. That'll clue me to which angles ought to be congruent. If this is the base, then these are the base angles, and they're the congruent fellas. It tells me that angle PRT is 130 degrees. Right there. I'm supposed to find out the numbered angles. Let me make a note about them. Angle 1, that's a supplement of 130. That'd be 50 degrees. What about the measure of angle 2? Well, angle 2 is the other base angle of that isosceles triangle. It's got to be congruent to angle 1. So it's also 50. Let's see the measure of angle 3 and 4. Angle 3, well, these two angles are each 50. That's going to tell you that this angle's got to be 100. But if these two angles are each 50, that leaves 80 for angle 3, huh? And therefore, if angle 3 was 80, now the picture's not drawn to scale, but that's okay with me. If this were 80, wouldn't angle 4 have to be 100? And I'd like for you to remember that this angle should equal those two angles added up. This one, by the way, should equal these two angles added up. And it does. Let's go to this next guy. M is the midpoint of AB. We ought to mark it that way. This guy's congruent to this guy. And CM is congruent to MB. CM is congruent to MB. AM is congruent to MB, and MB is congruent to CM. I guess all three of those segments must be congruent. So this would be an isosceles triangle, and this is another one. I have a couple of isosceles triangles to work with here, and this angle is 25 degrees. Angle 1 and angle A are base angles of this isosceles triangle. Angle 1 would also be 25. What about angle 2? Well, that's the vertex angle. 25 and 25 gives me 50. That would leave 130 for this one. Angle 3 would have to be 130. And angle 2 should have been 130. Getting a little ahead of myself with angle 3. Angle 3 is going to have to be 50, the sum of the remote interiors. Now what about angle 4? These are not the base angles. Since these are congruent sides, these would be the base angles. Angle 3 we found to be 50. That leaves 130 for these two to share. And if they're going to share it equal, it's going to be 65 for this one and 65 for that one. So I get the measure of that angle to be 65 degrees. It does ask me about the measure of angle ACB, this one ACB. I know that this was 25, and I know that this one was 65. Right there, wasn't it? Yeah. And if that's true, then those are going to add up to 90. I expected that to be a right angle from some stuff we're going to know from the second semester. Let's go down the page a little. Triangle ABC is isosceles with base BC. This is a really simple question, but you need to make a sketch. Make a quick sketch. AB is isosceles with base BC. If this is base BC, and here's the vertex angle A, and it's 40, huh? They would like to know the measure of angle C, which is one of the base angles. I'm using the triangle sum theorem. I know all the angles will add up to 180. 40 went there. These have 140 to share. And they're going to share it equally. The measure of angle C would be 70, as would be the measure of angle B. Another one, kind of like the other one, but a little bit different. Let me sketch it like this. Triangle PQR is isosceles with base PR. Let that be my base. And angle Q is my vertex angle. And if it is base PR, let me mark these to be the congruent legs. And these are my congruent base angles. Angle R is 40? Okay. I want to know about the measure of angle Q. But if angle R is 40, wouldn't angle P have been 40? Base angles of an isosceles triangle. And there's 80 together. I guess that leaves about 100 degrees up here, huh? For the measure of angle Q. So I'm using the isosceles triangle theorem and the triangle sum theorem. Get a couple things figured out. Here I have a rectangle. And we have not talked as much about rectangles, rhombus, squares, and trapezoids as I wish, but let me tell you a couple things about the rectangle. It has congruent diagonals. I'm sure that if this is a rectangle, that AC and DB must be congruent. Also, they bisect each other. This segment is congruent to that one, it's congruent to that one, it's congruent to that one. So you got 4 little isosceles triangles hidden in here. Let the measure of angle ACB be 65. That's this angle right there, 65 degrees. And this triangle XCB is isosceles, and these are the base angles. So angle 1 would also have been 65. I'll label that here. That angle would have been 65 right there. And I know that these two angles make a right angle together. They must be complementary. They got to add up to 90. That forces this angle to be 25. The measure of angle 2 has to be 25 degrees. This is an isosceles triangle right there. These are the base angles, so this angle would have also been 25. And since these add up to 90 together, yeah, I think this angle's going to be the complement of 25. There's another 65 right there. Yeah, I think that's angle 4. Got to be 65. And it makes sense to me that this angle and this angle would be congruent, because with these parallel lines, those are alternate interior angles. They would have to be congruent. I gotta go find out about angle 3 though. A couple ways I could. If this was 25 and this was 25, then those add up to 50. So what about this angle? If I take that 50 out of the 180, that leaves 130 for this angle. And these are vertical angles. Yep. So I think the measure of angle 3 would also have been 130 degrees. I got 25 here and 25 there. There's 50, leaving 130 for here. Of course, in the vertical angle part, it'll be 130 as well. Here's a pretty simple question, but it's not so simple if you don't have a sketch. Let's do that. Let's make a sketch right away. Isosceles triangle, PQR with base QR. Now I got a good opinion about who's going to be the congruent angles here. Angle Q is 8x plus 2. And angle P? No, I don't know about angle P yet. Angle R is 6x plus 14. Well, those are the base angles of this isosceles triangle. The base QR, yeah, these are the legs. Those are the congruent angles. So it must be true that 8x plus 2 is the same as 6x plus 14. Let's see what that brings us. I'll subtract 6x from both sides, and I got 2x plus 2 equals 14. Subtract that 2x from both sides. I guess I got, subtract that 2 from both sides. I guess I got 2x equal to 12. So x is equal to 6. Bear that thought in mind. Let's figure out about it. Well, we're supposed to know about some angle. I don't know which one. Let's figure out about what we could. Angle Q, if x is really 6, 8 times 6 is 48 plus 2 would be 50 degrees for angle Q. That's good to know. What about angle R? It ought to be the same. 6 times 6 is 36 plus 14. Yeah, there's another 50. I figured they might have wanted to talk about angle P. What would be the measure of angle P? Well, if this one was 50 and this one was 50, there's 100, so I guess that would leave 80 up there. That way I get 180 inside of that triangle. Same kind of an idea here, but not exactly the same. Let me make another sketch. Talks about an isosceles triangle with vertex angle C. And it's triangle ABC. If this is my vertex angle, these are the legs. Here's the base angles. And what do I know for sure? Angle C is 5x plus 5. Angle A is 10x. And what can I do with these? Those aren't going to be congruent to each other. These guys would be congruent to each other. I understand that. The base angles would be congruent. So this is also 10x. Maybe there is something I can do with those. Yeah, I guess I could use the isosceles. No, I have used the isosceles triangle theorem. I know that those would be congruent. But now I can use the triangle sum theorem. Add them all up to 180. See what we find. Yeah, 10x plus another 10x plus 5x plus 5 adds up to 180. So I have 25x plus 5 equals 180. Let's subtract 5 from both sides of that, get 25x equals 175. Divide both sides by 25, and I got x equal to 7. Let's see about these couple of angles. If x is truly 7, 5 times 7 is 35, plus 5 is going to be 40 degrees for angle C. About angle A, it'd have to be 70 degrees. How's that working for me? 70 here, it'd have to be 70 for angle B, wouldn't it? Those are base angles. That would be 40 up here. That does work well. Yeah. You want to find the measure of angle B? I'm prepared for that. Angle B, he would have been 70 degrees. Like angle A was. I know in this last picture it is not drawn to scale. That's okay. We should not judge this picture by its appearance. We're told that Q is the midpoint of PR. I'll mark it that way. That looks okay with me. Angle P is supposed to be 55 degrees. And also SQ is congruent to QR. SQ is the same as QR, and QR is the same as PQ, so all three of those segments are congruent. Yeah, this one's got to be isosceles, doesn't it? I was supposed to find all the numbered angles. I don't even got any numbered angles. Let's put some numbers in here, 1, 2, 3, and 4. Figure all those guys out, and we'll be in good stead. These are the legs. These are the base angles on this, the base of this isosceles triangle. So angle 1 would have been 55. How about angle 2? Well, angle 2 is an exterior angle. If this were 55 and 55, this must be 110. You could have figured out 55 and 55, subtract from 180, leaves that one to be 70. Take that out of 180, and angle 2, that would have been 110. Equals the sum of the removed interiors. But now this angle is the vertex angle of this isosceles triangle. These must be the base angles. And if this angle was 110, let me get that in place before I forget it, then these two angles would have 70 to share. Yeah, these two angles should add up to that 70. It must be 35 a pop. Measure angle 3, 35, and the measure of angle 4, also 35 degrees. But then it does ask me about the measure of angle PSR. And I haven't even done this yet, but I know it's going to be 90. I know in this circumstance, this angle will always be 90. When we talk about circles, I'll be able to prove that to you. But for right now, let's make sense of that. This angle is 55. And this angle, how big was he? Yeah, that one was 35, wasn't it? And 55 and 35, yeah, that adds up to 90. That should have been a right angle right there. Measure of angle PSR, 90 degrees. So here's a couple things about the isosceles triangle theorem. You've got a few things to work on yourself. Thank you. Do a good job, and you ought to take a test this week too.